Hello. Of all the lessons that I would teach this year, if I were to pick one that I didn't want to try to teach with you guys not physically in the classroom with me, this would probably be it. Okay, I am going to attempt to teach you guys how to find the volume of a revolved solid using calculus. So, for example, imagine that we have a vase. I want you guys to picture like a line straight down through the middle of it. And this vase is symmetrical the whole way around. So if you can look at this vase and think about it two-dimensional, if we had equations for the outside edges, if we had the functions for the outside edges of this vase, and we knew the line that went down the middle of it, we can try to then transform it into 3D and picture it and play with it and figure out what the volume is inside of that. Okay, now there are going to be 3 different ways that we can do that. I'm going to show you 2 of them today, and the only reason I'm showing you 2 is because they are used in different circumstances depending on the shape that you have. Okay, now I really wish you guys were here with me because we would be playing with Play-Doh together, because one of the most important parts to be able to do the disc or washer method is to be able to visualize the shape that you are trying to find the volume of. Okay, so we're going to start with a 2-dimensional shape, and then we're going to try to turn it into 3 dimensions. Okay, so imagine that we are taking, don't even worry about what the words are called right now. Imagine that we are taking the y equals square root of x curve. Okay, so we have a working knowledge of what that looks like. Now, let's say I decided to give you some bounds. So let's say we are only going to look at that curve between y equals 0 and x equals 4. So y equals 0 is the x-axis. X equals 4 would be a vertical line right here. And so we are only then looking at that 2-dimensional shaded region. Okay. Now, depending on what line we want to revolve this shape around, it's going to turn into a different shape. So let's say that we decided to revolve this shape around the x-axis. So we're pretending that this is, we're going to call this our axis of symmetry, the line that we revolve around. So picture in your head that you revolve that all the way around my arm. It would be flat on the bottom. It'd be a little bit of a mound up. Now, I tried to kind of create this with Play-Doh for you, but I didn't do a real super good job. I didn't spend a lot of time with it. So imagine that it's flat on this side, it curves this way. This isn't a real super good example. But what I am here to share with you is this. Okay, so here's where we're gonna like put a whole bunch of stuff together that we've done. Okay, what you're gonna see me do on my picture is I'm gonna usually do this. That's gonna be my axis of symmetry. Okay, that's the line that I am going to revolve my 2-dimensional shape around. The idea behind this is if I make slices, if I take slices of that 3-dimensional shape perpendicular to my axis of symmetry, I want you to think about what the shape would be. So remember, this goes all the way around. If I cut this, so let's say that I take an illegal device like a knife, I'm going to cut it perpendicular to my axis of symmetry. What you would see turns into, if it didn't smush when I cut it, is when I cut it like this, and then we look at it, it's a circle. Now, if I cut it down here, it's a bigger circle. If I cut it up here, it's a smaller circle, and all sorts of places in between. Now, we're going to use that idea of the fact that I know how to find the area of a circle. The area of a circle is pi r squared. So we are going to take all of the circles. So we are looking at, so here's the idea of an infinite number of circles. So if we took an infinite number of slices and added up the area of all of those circles, we would have the volume of our revolved solid. And so if we think about when we add up infinite things, like when we added up infinite rectangles to find an area, we took the limit as x approaches infinity. Okay, same idea here, and we're really doing, so we're going to say the area, or actually we're doing the volume of our three-dimensional shape is going to be the sum, and by doing the infinite sum, it ends up being the integral of our function, so pi, and then we're taking our radius squared, pi r squared. Now, depending on if we have a horizontal axis of symmetry or a vertical axis of symmetry, it's going to make a difference what my bounds are and if this function needs to be in terms of x or y. So if you have a horizontal axis of symmetry, then these bounds are in terms of x, so your function will be in terms of x. And so if we had a vertical axis of symmetry, it's the same equation, but instead of a and b, I'm going to say c and d. Those are in terms of y. So if I said, okay, this is a and b, x values c and d, so this would be the point like b comma d. This would be the point a comma c right here. This is b comma 0. So CD, since those are my y values, this function would need to be the radius in terms of y. And so you're going to see me writing dy there like that. So in this particular case, if I wanted to use this method to find the volume of this curve, of this shaded region revolved around the x-axis, I'm going to go pi, antiderivative of my x values, so it would be 0 to 4 of my function written in terms of x, root x squared dx. Could we then go through, solve and simplify this? Yes. For our purposes right now, I'm just going to go through and help you write these equations. Now, second question. Let's take exactly the same setup, and instead of revolving around the x-axis, let's revolve around the y-axis. And this is going to change, even though all of this is the same, the picture is the same. Depending on what we revolve around, it changes the way that you approach it entirely differently. Okay, so let's actually, instead of a's and b's on this, I want to write down what my actual values are for this particular problem. My important vertices points here, we've got 0, 0, we've got 4, 0, and we've got 4, 2. Since my function was a square rooting function, the square root of 4 is 2. Okay. Now, if I instead want to revolve this around the y-axis, so this time, instead of revolving it around the x, let me just make that the x-axis again. I want to revolve around the y-axis. Try to picture what's going to happen then. If I'm revolving here, picture what happens like on this side. It's going to be like a cylinder on the outside, but it cuts down on the inside like that. Again, I did not do a very good job drawing this or molding this. It's going to be height. It's going to be the same height the whole way around the outside. This would kind of be if you saw the inside of it, if I cut it in half. But it's going to have an indent on the inside, kind of like, you guys probably too old for you, but like an ashtray in the olden days. If I were to slice this one perpendicular to my axis of revolution this time, since it indents down in the middle, gosh, this Play-Doh is too squishy. If I do this, oh, this is